Hi everybody, welcome back to the next part on video coding and more on motion and compensation and its accuracy. So last time we saw several methods to obtain a good motion estimation with reduced complexity with an efficient search and with the possibility of sub-pixel accuracy. The question now is, how does the search area, the search process and the accuracy affect the compression performance? Question mark. So a comparison of different search window sizes for the resulting total sum of absolute errors, SAE, can be found in the book Richardson Video Codec Design. So last time in this example, the Python example, had a search area of ±8 pixels. Right, rather small search area. So here we can see the influence of the search area on the compression performance, which is interesting for codec design. So there, in this book there is a comparison with an example video. This comparison was made with 16 by 16 block sizes, so 16 by 16 pixel, so I should say pixel block sizes, for the motion compensation. So, for instance, full search motion estimation. Right, so we have bigger block sizes here than in my example. In my example, we just had 8 by 8 pixel blocks. Here we have 16 by 16 pixel blocks, which means we only need to compute half as many motion vectors horizontally and vertically compared to the 8 by 8 pixel block sizes. So it's already a reduction in complexity this way. So now we want to check the influence on compression performance. So for that we need to take a natural video. So that was done here for this book. They took a natural video and tried different schemes and see what compression performance was obtained. So first, the case without motion compensation. Right? We just take the difference between two consecutive frames without taking into account their motion. So this works fine if we have no motion, like a still image, but other than that it's not really so great. So here we get the total sum of absolute errors. So this is not the mean absolute error, but the sum of absolute error, which means we don't divide by the number of pixels in the end, and that's why we get such large numbers here. But it doesn't really matter because we're only interested in the minimum, or how low we can get, right, in the relative change. So here we get the sum of absolute errors of 1.3 million. Right, 1,326,783. So that's the starting point here. So the number itself doesn't say much, but how much we can reduce it. So now with motion compensation, and now a tiny search window, just ±1 pixel. So our little experiment last time was actually much better with the ±8 pixel. Here we just have ±1 pixel. Minimum complexity. But we see we already get a reduction, right, to 1.278 million. So it's a small improvement, but the number of operations needed for the motion compensation is already 1 million, hence fairly high. Right? So we get a small improvement, but it costs a lot, 1 million operations. So I assume this is the arithmetic operations here. So then we have increased search window, ±3 pixel. So that's pixel again. So it's still not great, but more than ±1 pixel. So here we go down from 1.2 to 1.173 million. So that's somewhat lower, but we considerably increase the complexity to now 5 million. So that's also not so great, but we shouldn't give up, right? So now we have a search window of ±7. So that's similar to our Python example, where I had ±8. So here we get a sum of absolute errors of 898,000. So it's now clearly lower than before. So that actually helps a lot to increase this search window. But the complexity really goes up, 23 million. Right, that's tough. So now we have a larger search window, ±15. So that's about twice as much as my Python example. And we reduced the sum of absolute errors a little bit. So you could say actually this ±7 is kind of a good choice, because the error didn't decrease that much. But again, that's something that depends on the video. If you have what kind of motion you have in the video. If you have normal motion, then you don't need much don't need a high search window. But say if you have sports video where you have fast motion, then the larger search window would actually benefit you more. Yeah, but this ±15 pixel is leading to a large complexity. So here 99 million. So we get fairly good compression at the cost of really high complexity. Yeah, but this was the most complex search method, the full search. So how does this compare with a more efficient search method? Again, we can find a comparison for the same video sequence in this reference with a search window of ±15. So that was the largest here for the fastest motion. So for the fastest motion, we get this sum of absolute errors of 897,000 and a complexity of 99.1 million, right? 10 to the power of 6. Then we compare to the three-step search, which I showed last time, where you first have a coarse search and then refine the search iteratively. There we get a worse sum of absolute errors, so it's not quite as good, but it's actually not that far off, right? You wouldn't say that it breaks. It's actually still working, but not quite as good. But then the complexity went down a lot. So here from 99 million to only 3.6 million. So it's about a factor of 30, right? So it's a huge gain in complexity. So here we can see that we gained a lot of complexity reduction using the three-step search, the hierarchical approach, but only pay a small price in increased sum of absolute errors. So remember here, we only have an increase from 897 to 914,000. Yeah, so this is the way to go. Yeah, and then we also have a choice of reference frames in motion compensation. So that can be seen here. So what we saw so far is forward prediction. We're using P frames, which means the prediction is based on past frames, P for past. Also more than one frame in the past is possible. Right? So what we saw is just the previous frame, but we could also get more precise motion estimation by including more distant past frames. The advantage here is we don't need any additional delay for our prediction because the past frames are already there. The disadvantage, for instance, for scene cuts, it doesn't work for the following frame because of missing similarity. So if we have all of a sudden a scene cut, then there's no relationship to the previous frame. For that we have backwards prediction based on future frames. So the advantage here is that it can be used if there's no or not sufficient similarity to the past frames. Disadvantage, we need a delay to wait for the future frame to predict from. So actually we need to wait for the future frame from our camera before we can make a prediction from it. And also we have to transmit the future frame to the decoder first before the decoder is able to reconstruct the frame before, right? And that means we need to have a delay right here. This is the delay. Then we can also have a bidirectional prediction, or B-frames. We use both directions to predict the current frame, for instance a weighted average of both directions, or taking the best of both. For each macro block of the motion compensation, so the 8x8 or 16x16 pixels, the encoder transmits a mode information. Mode A is forward prediction, mode B is backward prediction, and mode C is the average of the two predictions. Right, so these are the three different possible modes, and if we are in B-frame mode, then we need to have an additional bit which basically tells which is which. Actually here we need 2 bits. So the advantage here is we obtain the best prediction because we have the most information as the basis for it. Right? We get the most precise motion estimation. It improves the compression efficiency by up to 50%. So actually this benefits a lot. Disadvantage, it needs site information for the signaling, and it needs delay for the future frame. Yeah, and then finally we have the iframes or the infraframes. There no prediction is used, no motion compensation. So this is used, for instance, at the start of the video or for resynchronization within the video, for instance, for broadcast. So no motion compensation used. The advantage here is that it's independent of other frames, can be used to start decoding the video sequence. So at some point we can start, and for the start we need an iframe. So that's also why it's important for broadcasting, because we need to wait, the receiver needs to wait for the next iframe to be able to start decoding it. The disadvantage here of the iframes is it needs the highest bit rates. So that's why you don't want to have many iframes. You only want to have as few iframes as possible. And that's also why it takes a moment for broadcast to be able to display a video stream, because the decoder needs to wait for the next iframe, and you don't want to have too many of those. Yeah, so that's depicted here in this picture. So here you can see the different types. Here's the current frame. You want to transmit this current frame, and this current frame now can have as a basis for its prediction future frames using backward prediction and past frames using forward prediction. Yeah, and in a typical coding sequence, for instance in MPEG video, those different types of frames are grouped in a so-called group of pictures, or GOP. The group of pictures is bounded by iframes on both sides and contains B-frames and P-frames in between. For good compression performance, we should choose only a few iframes, many B-frames, and a few P-frames. A video sequence consists of many consecutive GOPs, so that also the decoder knows which is which. So here we have a group of pictures, starts with an iframe, ends with an iframe, and then we have B-frames, P-frames, B-frame, and P-frame. Right, and you can see here the iframes stand on their own. Then the B-frames have as the P-frames have as reference here. Let's see, how does it work? So here the iframe is used as the basis for prediction for the B-frame, here this B-frame, and this P-frame, right? So the arrows depict where this iframe is used as a prediction. So this would be the reference for these frames, including the motion vectors, right? So this iframe is a source of B frames and P frames. Then we have, let's see, this P frame is also a source for the neighboring B frames here. But also this P frame was predicted from this previous I frame. So you can see this arrow goes from this I frame to this P frame. So this P frame was only predicted using this past I frame in this case. Right? And we cannot use those B frames as prediction for this P frame because we use this P frame to predict those B frames. So we have to decide which direction. So here this B frame, for instance, is predicted from this coming P frame and from the previous I frame. So it has those two sources of prediction. Here this B frame has only the coming P frame as the basis of its prediction. Right. Yeah, so and this sequence is basically then repeated for the duration of the video. So we have many of those group of pictures which repeat over and over. Yeah, and the longer this group of picture will be, the more efficient the coding will be. But that also means the more sparse the iframes will be, and then we have to wait longer before we can decode. Right. So observe that predicted frames can only reference already reconstructed frames. That is why referencing B frames is problematic, because they are reconstructed last. So here an example, we have an I frame, a P frame, two B frames, another I frame, a P frame, two B frames, and so on. So that shows that each GOP is separated by an I frame from the other. So each time we have an I frame, that's the start and the beginning of a GOP. Yeah, and then we can have enhancements to the motion model. So we can have variable block sizes. So depending on the image content, it might be useful to use different block sizes. For instance, 16 by 16 pixels, 8 by 8 or 4 by 4. And ideally this would be adapted to the image content. Right? If you have small moving objects, you want to make the blocks small. If you have large moving objects, you want to make the blocks large. This is used, for instance, in H.263 and H.264 and also H.265. So the latter also offers the flexibility of subdividing those blocks, so 64 and 65, into rectangular subblocks. So 4 by 8 or 8 by 16. So again, this can be used to adapt the block size to a moving object. Yeah, and then we could have complex motion models. Picture warping can be used to take into account the effect of zooming in or out, or rotations of objects. But it also leads to an increased complexity in the encoder and also the decoder, right? Because that means we not only have to search for the position, but also for those warping coefficients or parameters. So it makes it quite complex, and that's why it's not really done. Then object-based coding and motion compensation. Here we don't have blocks, but find out the boundaries of our moving objects in the scene and apply motion compensation to it. So that means to the entire object. So the entire object would be a big block, but not rectangular, but shaped like this object. Theoretically, this is very efficient for the motion compensation, but very computationally complex, especially for the encoder. This is one of the reasons this approach is still an active research area. Yeah, so in theory it's nice, but in practice you have to actually detect objects, and that's quite complex. Okay, so that brings me to the end of this set of slides. Yeah, thank you for the attention and see you next time.